Deep space travel subjects the human body to extreme gravitational forces. To prepare for the pressure of a rocket launch, astronauts must train in industrial centrifuges that simulate the crushing weight of high-speed acceleration. We are applying those same aerospace standards to a much smaller pilot, a hamster entering a high-stakes training cycle. This is the training apparatus, a custom-built metallic centrifuge maze. It features a circular track designed to create a disorienting deep space environment for our tiny pilot. The maze contains several engineered hazards, glowing LED corridors, shifting internal walls, and a series of pressurized airlocks. Our pilot is geared up for the run. The goal is to see if he can navigate these obstacles successfully, or if the rotational force will cause him to lose his footing. This mission tests how a small mammal's biomechanics and spatial awareness hold up under the stress of artificial gravity. The launch sequence begins as the hamster enters the first airlock. The centrifuge activates, rapidly accelerating the entire maze into a continuous spin. This diagram shows the physics of the spinning gauntlet. As rotation speed increases, artificial gravity pushes the pilot outward against the maze walls. To increase difficulty, inner walls pivot, narrowing the path right as the outward gravitational pressure is strongest. The pilot reacts by lowering his center of gravity. He widens his stance and digs in his paws to stay balanced against the sudden centrifugal pull. Successfully clearing this first sector demonstrates that the hamster has the reflexive equilibrium needed to stay upright while the floor moves beneath him. Inside the maze, the view is a disorienting blur. LED streaks of light flash past as the pilot sprints through the metallic corridor. The core challenge is maintaining speed. The pilot has to push forward, even as the rotation of the maze tries to pin him against the outer wall. This skeletal overlay shows how he manages vertical climbs. He uses his rear muscle groups to generate upward force, overcoming the downward pressure created by the centrifuge's rotation. When the path drops into a slide, he braces his limbs against the metallic surface to control his descent and prevent a collision. He succeeds by keeping his weight low and distributed evenly, allowing him to stay mobile despite the forces acting on his body. The mission now shifts from a physical sprint to a test of focus. As the pilot reaches the pressurized airlock chambers, he must wait for the signal light to change from red to green. This requires him to suppress his urge to run and wait for the door to actually clear the path. In the next sector, he enters a simulation of zero gravity. He has to judge the distance between these hovering platforms and jump precisely to avoid falling into the gaps below. The run reaches its peak at the final turn. The centrifuge is now at maximum speed, forcing the pilot to navigate a complex corner while under the highest physical load of the mission. Completing this turn shows that the pilot can still process spatial information and solve the route even while his senses are under significant pressure. With the obstacles cleared, the centrifuge begins to decelerate. The spinning slows until the maze finally comes to a controlled stop. The final airlock door opens, and the pilot sets foot onto the simulated lunar surface, marking the end of the mission. This chart compares the pilot's speed to the centrifuge's acceleration. Even as the rotation speed increased, his pace remained steady, showing he didn't let the gravitational force slow his progress. The data confirms that the hamster's natural spatial awareness allowed him to adapt to the spinning environment almost instantly. To mark the successful training cycle, our astronaut is moved to a recovery pod for a well-earned reward. This mission proves that high-level navigation is possible, even under intense physical pressure. To see our next deep space animal simulation, subscribe below.